Hello everyone, I am Sri. Today I will be introducing our project titled Timetable Generation. The core objective of this project is to design a fully automated timetable generation system. This system must ensure no student is assigned to classes at the same time. Faculty members are not double booked, classrooms are not overbooked, and are assigned appropriately. To achieve this, the system considers a variety of input data. Student registration, which includes the subject-wise enrollment, course structure, including LTP breakdown, that is, lecture, tutorial, and practical, faculty allocations per course, and room availability and their capacity. The other constraints we need to consider in this are all classes must be scheduled from 8 a.m. to 6 p.m., and there should be a mandatory lunch break in between. A classroom, a single room student faculty cannot be assigned to more than one session at a time, and practical sessions must be scheduled consecutively if their duration is 2 or 3 hours. If a course has three lecture hours per week, flexible splitting mean you don't have to schedule all the 3 hours consecutively. You can just split them as three separate hours or 2:1 ratio. Only lab rooms must host the practicals, and classrooms must meet the minimum capacity required by the number of students. These are the hard constraints which are to be strictly followed. In addition to these, in addition to satisfying these hard constraints, we also focus on optimizing using the soft constraints, in which we aim to minimize the lecture gaps and also avoid early morning and the late evening slots, reducing unnecessary room switching. Although these preferences are not mandatory, adhering to them enhances student and faculty convenience and leading to a higher quality timetable. Uh, the solution approaches. To tackle this problem, we implemented and analyzed three distinct methods, that is, Z3 solver based on CSP and A star and a meta heuristic approach using genetic algorithms and simulated annealing. CP SAT solver using Google's OR tools. Now let's begin with a Z3 solver. Z3 solver is a SMT solver. We break we first break down each subject into individual sessions based on its LTP structure. For example, a subject has three lectures, one tutorial and one practical, becomes five separate sessions. These sessions are the individual fund units we schedule. Each session is then decided with a set of decision variables: DI, SI, FI, RI, and delta I. DI is for the day of the session, SI is for the time slot, FI is the faculty of that particular session, RI is the room assigned for that session to happen, and delta is the duration of that particular session. Now let's talk about the hard constraints. These are non-negotiable. Violating any of these would make the schedule invalid. Every session must fit within a daily time slot, which ranges from S0 to S8. If the session lasts multiple hours, we must make sure it doesn't exceed the beyond the available time. A faculty member assigned to each session must be the one who teaches that particular subject. Therefore, FI belongs to faculty list of that particular subject. Student conflict. No student should have more than no student should be assigned to two sessions at the same time. Similar logic can be implemented for the faculty and the room conflict also. All the practical sessions must take place in the lab, and every class must be in a room that handles the number of students enrolled. Intra-subject non-overlap. Finally, sessions belonging to the same subject like lectures and tutorials should not overlap with each other. These constraints form the foundation of our schedule logic and are strictly enforced across all solver approaches. Next is the soft constraints and optimization. Now we have looked the hard constraint. Now let's look at the soft constraints, which help us improve the overall quality of the timetable. The first soft constraint focuses on minimizing gaps in the student's daily schedule. For example, if a student has a class at 9 a.m. and another one at 2 p.m., but nothing in between, that's a gap we would like to avoid. So for that, we calculate the gap, which includes max minus min plus 1 minus occupied, which gives the amount of unoccupied slots on that day for a particular student. This should be minimized. And one more soft constraint we consider is that avoiding the early morning slots and the late evening sessions. If any class is scheduled during the slots, a penalty is imposed. We need to minimize this penalty as well. Let's look at how we actually guide the solver to optimize the timetable. The optimization function we use is minimizing that 10 into total gaps plus 20 into early or late schedules. In our system, the hard constraints are strictly enforced, meaning the solver will never return a timetable that violates them. The optimization function only handles the soft constraints, best timetable among all the valid ones, one that reduces the lecture gaps and avoids the extreme time slots. The second approach is a meta-heuristic and a meta-heuristic based approach, which includes genetic algorithm and simulated annealing. In this approach, we implemented genetic algorithm, which is inspired by natural selection. We begin with a population of random but valid timetables. Each presentation has each represented at chromosomes, especially a sequence of session assignments. We then evolve these schedules using two operations. One is crossover and another is a mutation. To avoid the invalid timetables, every mutation we check against the hard constraints like avoiding student overlaps, ensuring room capacity. Now, a genetic algorithm is powerful, but it sometimes gets stuck in the local optimum. To overcome this, we integrated it with a simulated annealing, which sometimes allows the worst solutions also with certain probability, which is again controlled by the temperature parameter. The key idea here is nothing but instead of finding a perfect solution directly, we iteratively refine valid timetables, optimize the soft constraints like lecture gaps and early late sessions. The first the third approach we explored is the CP-SAT solver, a part of Google's OR tools, a powerful constraint programming engine designed for scalable scheduling programs. In this method, each session, whether it's a lecture, tutorial, or a practical, is assigned a combination of time slot, a day, room, and a faculty member. Here also the constraints are same as discussed in the previous slides, but they are encoded as the rules. The one of the biggest strength of CPSAT is that its native support both it natively supports both hard and the soft constraints. Why CPSAT works best? Because it combines speed, flexibility, and built-in optimization. CPSAT performed best on larger inputs, giving us the fast results while satisfying all constraints. So now my teammates will provide a detailed dive into the implementation and the unique features of each of these approaches discussed, that is Z3 based, A star and a meta heuristic and CP SAT solver. Thank you.
Hello everyone, I am Anirudh Kandwal. In this segment, I will walk you through the meta-heuristic techniques we used in our timetable generator for IIT Patna, specifically the evolutionary algorithm for satisfying hard constraints and simulated annealing for soft constraint optimization. Let's start by discussing how we address hard constraint violation in the timetable using an evolutionary algorithm approach, specifically a 1 plus 1 evolutionary strategy. Our objective here is simple: repair any violations of hard constraint to ensure the feasibility of the timetable. The processes begin by selecting the class with the maximum number of conflicts. These conflicts could be overlapping sessions, incorrect room types, or session scheduling during lunch. Next, we mutate the selected class, either by changing its assigned room or its time slot. We then evaluate the new configuration. If the result in the fewer or the same number of conflicts as before, we accept the change. To avoid getting stuck, we adapt the mutation rate using Stifle's rule, which adjusts based on recent success rates, increasing if changes are helping and decreasing if not. This loop continues until either all constraints are satisfied or there have been no improvements for several iterations, signaling a plateau. Here are key hard constraints we aim to satisfy. First, no overlapping sessions for any students, faculty, or room. Second, sessions must not span across the lunch break from 1 p.m. to 2 p.m. Third, we ensure that classrooms are appropriate for the type of sessions. For example, lectures shouldn't be scheduled in labs and vice versa. Lastly, practical sessions should be scheduled consecutively, ensuring continuity and avoiding awkward gaps. Violating any of these constraints makes the timetable invalid, so these are prioritized in the evolutionary repair phase. Once we have a feasible timetable that satisfies all hard constraints, we move on to improving its quality by optimizing soft constraints. For this, we use simulated annealing, a probabilistic technique we inspired by annealing process in metallurgy. The cost function we optimize includes gaps between classes which we want to minimize, sessions that are too early in the morning or too late in the evening, the number of rooms which is a student or faculty has to make, and overall idle time for everyone. We tweak the schedule by randomly moving one class at a time. If the new configuration has a lower cost, we accept it. If the cost is higher, we might still accept it, but with a certain probability that decreases over time. This helps in escaping local optima. The effectiveness of simulated annealing depends heavily on its temperature control. We start with a high initial temperature, which allows the system to explore a wide range of configuration, even suboptimal ones. This helps avoid getting stuck in a poor local optimum early on. The cooling schedule gradually reduces the temperature after each iteration. Specifically, we use the formula T is equal to T into 0.99 over approximately 2,500 iterations. The system becomes more selective, favoring only the best improvements. The final outcome is a balanced, student friendly, and efficient timetable that only meets all constraints but also provides a smooth daily schedule with fewer gaps, less waiting, and better room allocation. I hope you understand this concept. Thank you.
Thank you, Amrud. Hello, everyone. My name is Asis Kumar Gupta. I will explain how I have used constant satisfaction problem approach with the Z3 solver to create conflict-free timetable. Let's get started. Let's first understand how I have modeled the problem. In the written in the Python code, I broke the problem into session. Each subject has session like lecture 0, tutorial 1, or practical 0. For each session, I created variable to decide day, which is from Monday to Friday, time slot, which can be from 8 a.m. to 6 p.m., splitting into 9 hourly slots, skipping 1 p.m. Room, which is a list of available rooms like classroom or labs. The next variable is faculty, which is the teaching faculty in it. The Z3 solver finds value for this variable that satisfy all our rules, ensuring a valid timetable. The input comes from CSV file listing student, subject, faculty, and rooms, making it super flexible. Let's now talk about domains. The possible values for these variables for each session, say S34 lecture 0. The variable day can be integer from 0 to 4, which is from Monday to Friday. Slot is also an integer which is from variable 0 to 8, that is from 8 to 9 a.m. and then 5 to 6 p.m. Room is another variable whose domain is an index from 0 to the number of rooms, mapping to the room names like room 66 or lab 80. The another variable is faculty, the index from a list of faculty like employee ID 3 or employee ID 81. These domains are defined in the generate.py using Z3 int variable, ensuring every session gets a valid assignment within these ranges. Let's now understand the constraints, the rules that make the timetable work. My code enforces no student conflict if two subjects share student like subject 34 and subject 27, their sessions can't be overlap in time and day. No faculty conflict. A faculty member, say employee ID 3, can't teach two sessions at the same time. Room exclusivity. The room can't host two sessions simultaneously unless they are mutually exclusive student groups, and we allow multiple sessions per slot if rooms differ. Number four is session duration. Practical span multiple slot, example 2 hours and must be consecutive. Room suitability. Labs for practical rooms must fit student counts. Sixth one is different days. A subject session like S34 lecture should spread across days and balance. We have also implemented the optimization. I've added soft constraints To minimize gaps between classes, avoid 8 a.m. or 5 p.m. slot, reduce room switches. These are enforced using Jet3's optimized class, which find the best solution. The final output is clean and practical. In the console, you will see the timetable by day, like Monday, 9 a.m., subject 34 lecture by employee ID 3 in room number 36. The second example is subject 27 tutorial by employee ID 81 in room number 52. It is saved to timetable output.csv with columns for time slots and days and cells listing like triplet. My could also generate table matrix.txt showing stats like total gaps, example 120 room switches, early late session, generation time, etc. Now let us look at the pros and cons of CSP. Why use CSP with Jet3? It is super reliable, guarantees all constants are met, so no sessions are missed. Flexible, easy to add new rules like lunch breaks. It is also optimal. Find the best timetable with minimal gaps and switches. Let's look at the cons. It is slow for big college problems. Solving large problems like 200 students can take large time. Memory heavy. Jet3 uses a lot of RAM for complex constants. If constants are impossible, it fails and you need to tweak them manually. Now let's look at the improvement and conclusion. To make this CSP method even better, I will try to speed it up, use incremental solving or parallel processing in Jet3, handle inflexibility, automatically suggest constant relaxation like adding rooms, add add weights, prioritize certain optimization like avoid 8 a.m. over minimizing gaps. The third one is integrating heuristics. Combine Jet3 with quick algorithms like A star for faster initial solution. Thank you.
Good morning, everyone. I am Arpit Kumar, and today I will be with through a work on timetable generation using a A-based approach. We will also compare it with other methods like J3 solver and C-sat solver. Here, A star based approach. A star is a path finding and graph traversal algorithm. It is a find the least cost path from the start state to a goal state. Here use a function fn equal to gn plus hn. Here gn is a cost function which is started to the current node, and h is a estimated cost from the current node to the goal node. Why used here? Is such an algorithm we are required state representation. uh, First is a state current partial timetable successor assigned to the next assigned subject to the slot will complete valid schedule with node conflicts. Here use this function for a state ordering for priority. Why used heuristic a star algorithm in this timetable generation? Our heuristic is a simple but effective gn counts constant violation and hn counts unsigned subjects. This ensure really priority states closer to valid full timetable with Python heap queue to maintain the priority queue in efficient way. Valid slot generation is subject to assign a slot, day, time, and room. These are constant. Room must be satisfy capacity constraint. Okay. Avoid time and room clash with each other assignments. Conflict check-in in assignments. Room over capacity checks. Room times collision checks. Faculty overlap constraint. Faculty I assume faculty threshold is 3 in our program. Scheduling loop summary. We start from the empty schedules and keep expanding the most promise a state successor are only added in their assignments is valid. keeping the search space manageable. Output and formatting. Our outputs file timetable dot output dot csv file, row and column and cells. Row time slots 8 to 9 something something, and columns day Monday to Friday, and each cell which subject is assigned. Challenges in a star based timetable scheduling. Challenges we faced include a state space, uh, design an efficient heuristic, handling complex constraint, and making the algorithm scalable. Managing different states and maintaining optimally we also critical. Comparison this table, this Z3 CSP, uh, JNS heuristic, and CSP and another online tools is OR tools. We also evaluate Z3 genetic algorithm with simulated annealing, and CP said Z3 is a precise but slower large input. A heuristic method are feasible and faster, while CP sets gives the best performance for larger scale real world timing. Conclusion: to conclude, all methods respect a hard constraint like avoiding students or faculty classes and owing room capacities. The optimization will CP set provided the best overall balance. Z3 remain best for a small stick scheduling. Okay, based on these slides, thank you. That's a summary of our work. Thank you for your times. I have been happy to take this question.